and the age greater or equal than 60, that person can retire, right? But what if it's not a male? Well, then we use an or. So I'm going to use an or. I could say, listen, I could say is male equals, it's not true, I guess, it's false is the same, and age greater than 55, and then this person can retire. Otherwise, keep working. And to do an else. And actually, I can make it slightly more efficient. Can you tell me how would you rewrite it to make your if statement a bit more efficient? Do you care to know the gender if the person is 60 years or older?
No.
All right. No matter what gender they are, they can retire. So instead of this, you could write it like this. You could say male equals false, or you can just put not male. And age greater or equal than 55. That's 1. Or the person is already over 60. It doesn't matter. So, if I'm here, I said 55 and it's false, right? But the computer does parentheses first, right? It's the order of precedence. And once that executes in a CPU cycle, and by the time it comes out of the parentheses, it doesn't know what was inside the parentheses. That's a next CPU cycle and forgot what it did before. So we have that is a female. So it comes here in the orange one. I'm doing the orange first. Just that's a CPU cycle. This is another CPU cycle, and then the two results are combined in the next CPU cycle. So it says is male equals false. This is an AND statement. Do I need to test the age? If this is false, and this is an AND statement, do I need to test the age? No, so the computer doesn't do that. That's called a short circuit evaluation, which means if it's a false and it's an AND statement, it doesn't need to keep testing. If we're doing the one above, so it's male, it's false equals false, yes. And the age is greater or equal than 55, it's true. Then this whole thing is true based on this. So if this is true, or do I need to test the age? No, because if an OR statement, So long as one of the two is true, the whole overall statement is true. I don't need to keep testing. It's already true. So, for instance, besides this, the one above, there are other things that you have to take in consideration if you can retire. You know how many years you worked, and if at some point did you get disability or something. So it's a big calculation. And there's a function somewhere, type Boolean, somebody wrote to do all the rest of the calculations. So let's say we're using that function and we call it can retire. It's a function that returns a true or false. If that function takes 5 seconds to run, I want to test the variables first, because if this is true, I don't need to run that. If I run the function first, and that function takes 5 seconds, and then I test the variables, and one of the variables is false, it kind of slows down the system, right? It's not efficient. So if you have, well, you will see that you're gonna see functions inside the if statement that return true or false. Make the functions the last. That way you test the variables first. Questions? This is hard. This is the easy part. The hard part in C is the pointers, at least to understand that concept. And then you go to Java, it's all pointers. And that's why I like to give you exactly what happens in memory, so when you go to my 114 class, you're not too lost. And then in my 114, I give also display how the memory works, so when you go to data structures, you're not lost, or so lost. Anyways, questions? Bless you. This is easy stuff. All right. Let's take 10 minutes then. All right. So where were we? Oh, if statements, right? So we're not going to cover everything today, but there's one more thing I want you to know. We said we use double and equals to compare one, right? To compare two values, because if we only use one, it's the assignment operator. So we use two ands to do a logical and, or logical or, right? Guess what happens if you only use one? What happens if you use one? You know what that's called? You didn't read the chapter, huh? Bitwise. What's a bitwise? Well, basically, it goes like going bit by bit, comparing two bits. If the two bits are 1, then the resultant bit is 1. if you're doing OR, as long as one of the two bits is 1, then the outcome bit is 1. So remember, we talked about ASCII codes, right? And I told you go to ASCII code twice.com. And there's a list of all the codes. And when you type on your keyboard, a number is transmitted, right? From 0 to 255. And when you type 0, it's actually 48 being transmitted. So, if I type capital letter A, what number is transmitted? If you look at that website, if you press your Alt key and using the numbers on the right, you type 65 and then release the Alt key, letter A shows up. So my last name has an accent on the O, I press the Alt key, I press 162, and that's how the accent is printed. So this is 65. Right? So 65 in binary, well, let's do our how do we convert 65 into binary? So this is really easy, right? So what's the power of 2 closer to 65 without going over? 64, right? Is that 2 to what? 2 to the 6, right? 64. So 65 minus 64 is 1. So what's the other? 2 to the 0 is 1, right? So that's how 64 is. In binary. So when you press the capital A, this is what this stream of bytes looks like when it's transmitted to your computer. If I want to make that lowercase a, if I want to do lowercase a, I can OR, do a bitwise OR. So bitwise OR, and I do this. So what number is that?
32.
That's 32. So if I do a bitwise OR, it says as long as one of the bits is 1, the outcome is 1. So what number is that? Well, it's easy. 64 plus 32 plus 1. That is 97. So it's like adding 32. So the computer, to add a number,